let's get going now with part B of this problem. We've got our long insulating cylinder in the middle, and concentric with that is a conducting shell. So we have a solid core, then we have some empty space, and then we have a conducting shell around it. Both the insulator and the conductor are charged. The insulator has a uniform charge density. It means the charge is uniformly distributed throughout its volume. The conductor is also charged, and the charge on the conductor is spread over the inner and the outer surface of the conductor. And that's what we did in part A. We found those surface charge densities. Part B says find an expression or an equation for the electric field inside the insulator, between the insulator and the conductor, inside the conductor, and outside the conductor. So we're going to use Gauss's law to calculate those electric fields. Let's get started on that process. Let's write down Gauss's law first. Says that the net electric flux through any closed surface is the integral of the electric field over that surface, and the net electric flux could also be given by the net charge enclosed by the surface divided by the constant epsilon naught. First thing you have to choose is what should our Gaussian surface be. If we have geometry of cylinders, then our Gaussian surface should be a cylinder. The cylinder will have radius r. Now in our geometry, we're going to take r at 4 different places. One case it'll be inside the insulator, one case it'll be between the insulator and conductor, once it'll be inside the conductor, and once it'll be outside the conductor. But in general, it's going to have radius r, and it's going to have length L. Let's have a look at E dot dA, where our Gaussian surface is a cylinder and our charged object has cylindrical symmetry. So if we have a charged object that has cylindrical symmetry, it means that the electric field comes outward everywhere from that line of charge. Negative charges would go inwards, of course. Then a Gaussian surface we would represent with a dashed line. Here I'll draw it outside this object. I'm just trying to show cylindrical symmetry in general, not necessarily this exact problem. So our net electric flux, what we're trying to do now is let's deal with this part of Gauss's law, and then separately for each of our 4 cases we'll deal with Q enclosed, because this part only depends on the geometry. So our net electric flux is equal to the integral of E dot dA. There will be 3 places where we can have electric flux. We can have electric flux on the front face. It's going to be the integral of E dot dA. The integral of E dot dA is the magnitude of E times the magnitude of dA times the cosine of the angle between E and dA. Our electric field vectors are radially outwards. Our area vector on the front face sticks out of the front face. It's perpendicular to the electric field. So if this pencil sharpener were my cylinder, the electric field vectors point out from the sides of the cylinder, and our area vector on this face points out this way. So those two things are perpendicular. Cosine 90 degrees equals 0. So there's our dA. The back face is the same as the front face. Because on the back face, our area vector, so our electric field still comes out this way, our area vector comes out this way, those guys are perpendicular. And then we're left with the tube part or the cylinder part, so this part right here. You could call it the tube or the wall. I'm not really sure what's the best word to describe that. Still the integral of E dot dA. The electric field comes out radially everywhere, and the area vector comes out radially everywhere. those two guys are parallel. If the electric field points in, it's anti-parallel and the flux would be negative. So cosine of 0 is 1. Our electric field anywhere on this surface, if we're a constant distance from the surface, will be a constant electric field. So we've got E times the integral of dA equals E times A. A refers to the area of this cylindrical surface, the wall part of the tube, which is 2 pi RL. So the net electric flux, given as the sum of the integral of E dot dA over each of the three faces, is 0 plus E times 2 pi R times L. Okay, we've got this part of Gauss's law done. Now, this part of Gauss's law is done. This will be true for all four of our places. Next, what we'll have to do is start to apply Gauss's law and find Q enclosed for each of our different spots. Okay, fresh sheet of paper here because we don't want to get messy as we go through our work. So first of all, let's do our Gaussian surface as a cylinder with a radius that's inside the insulator. So I'm going to draw my Gaussian surface first. I'm going to do my work. I'll go in red for when we're inside the insulator. So my Gaussian surface in a 3D image will look something like this. Actually, let's stay completely inside. We don't want to get near to the edges because it's a long cylinder. So for our inside the insulator, here's our Gaussian surface. This is what it looks like in 3D. From a front view, looks kind of like this. That is not the most concentric circle I've ever drawn. That's got radius R. That's got radius R. And the radius of our cylinder, of course, was capital R. Okay, so let's apply Gauss's law to this situation. When we apply Gauss's law, Q enclosed means the charge enclosed by the Gaussian surface, which means how much charge is inside this little cylinder that I just drew. Okay, so for my situation, R less than R, I know that my flux is E times 2 pi times R times L. Next, I want to find my Q enclosed. Well, the amount of charge inside this cylinder is just going to be the density times the volume of that little cylinder. So rho is the density. That was a constant and that was given. This V is the volume of the Gaussian surface, which was a cylinder with radius R and length L. So that's rho times pi R squared times the length L. Okay, we know our flux from Gauss's law. It's the integral of E dot dA equals Q enclosed over epsilon naught. Let's fill in everything at this point. The integral of E dot dA is E times 2 pi RL. Q enclosed is rho times pi R squared L. Don't forget to divide by epsilon naught. Things that cancel are pi and L. We are left with the electric field equals, oh wait, we've got an R here and an R squared here, so one of those cancel. We've got rho over 2 epsilon naught times R. The charge on our cylinder is positive, so the electric field is going to be radially outwards. When R is equal to the radius of the insulator, then we'll just put in a capital R here, and that would be the electric field at the surface of the insulator. Okay, so that's inside and on the surface of the cylinder. Let's look at the next place we wanted to find our electric field. The next place was for R in between the cylinder and the conductor, so somewhere here in this white space. Okay, let's draw another Gaussian surface. I'm going to pick a different color. I'll take brown for this one. So r less than r less than r of the inner surface. R of the inner surface of the conductor is here. So this time our Gaussian surface is going to be another cylinder. It's got length L and radius r. Okay, so now we're going to use this as our Gaussian surface and apply our Gauss's law. R less than r less than ri. Gauss's law says that the net electric flux is the integral of E dot dA. We know that this is E times 2 pi RL equals Q enclosed over epsilon naught. We have to find our Q enclosed. Okay, Q enclosed this time, it's still going to be density times volume, but it's only the volume of the insulator that's within the conducting shell. Our Gaussian surface is bigger than the insulator, so the stuff outside the insulator doesn't have any charge at all. So when we do our charge times volume, it's just the volume of the stuff that has charge, and that would be the insulator. Oh, sorry, the dog got excited by something. So rho is our density, V is volume of insulator inside the Gaussian surface. In the previous part, that was only a fraction of the insulator. This time it's all of the insulator that's inside that. So that's going to be rho times pi r squared. So we only go up to the size of the insulator times the length. Let's put it all together. So the integral of E dot dA is E times 2 pi r times L equals charge enclosed rho pi r squared L divided by epsilon naught. Pi cancels, L cancels, and we'll solve for E. E equals rho times r squared over 2 epsilon naught times 1 over r. The insulator has positive charge, so the electric field is going to be radially outwards. Okay, so we're halfway done. The next part is really easy. Find the electric field where r is in between the inner and outer radius of the conductor. So find our electric field inside the conductor. That's one of our conditions of static equilibrium. We'll do a Gaussian surface for that one. So our Gaussian surface is going to have to be a surface inside the conductor. I'm drawing them bigger and bigger so that my picture doesn't get too messy and you can see all of the different pieces. So that's the radius of my Gaussian surface. So Ri less than R less than Ro. Do this one in green. This one is just something you're supposed to know off the top of your head. So if Ri is less than our Gaussian surface radius is less than Ro, it means we're inside a conductor in static equilibrium. That tells us that the electric field equals 0. Anytime you're in a conductor in electrostatic equilibrium, the electric field has to be 0 because equilibrium means that the charges are not moving, so the acceleration is 0. If the acceleration is 0, then the force is 0. If the force is 0, then the net field has to be 0. So anytime you're in a conductor in electrostatic equilibrium, the net electric field has to be 0, and it's okay to just state that result. Okay, last one is, what is the electric field outside of everything? So what's the electric field out here? This time our Gaussian surface is going to be a cylinder out here. So let's draw those on our picture. The last color we have to go with is blue. So our Gaussian surface is going to be a cylinder outside everything. Okay, it's got length L and radius R. And this is for R greater than RO. Now I realized I missed some on my two-dimensional version. Just fill those in now. You can draw in 3D or 2D. It doesn't really matter which. Just make sure you label clearly what it is you're doing. And then the last one was in brown. Okay, there's all of our surfaces drawn for everything we've done so far. So this is our last one. We're outside of everything. So when we do our Gauss's law, we're going to have to add up what is the charge inside this blue circle, this blue cylinder. The charge inside this blue cylinder is going to be the charge on the conductor plus the charge on the insulator. It's going to be a little bit of a funny way to write it down, but try and keep that concept in your head, is that we're just adding the charge on the insulator and the charge on the conductor. So we're adding these two guys together because those are the only charged objects inside our Gaussian surface. So that's where we're going with this now. So R outside the conductor. We're still going to apply Gauss's law. The integral of E dot dA is our net flux. We know that that's equal to E times 2 pi RL. And that's going to be the Q enclosed over epsilon naught. Let's just be careful about finding that Q enclosed. So Q enclosed equals Q of the insulator, INS for insulator, plus Q of the conductor, CON for conductor. Okay, so how are we going to find the charge on the insulator? That's just going to be density times volume of the insulator. So that's density times pi r squared L. Charge on the conductor, also going to be density times a size dimension, but let's look at what density we're given for the conductor. The conductor carries a net charge per unit length. We have a linear charge density here, so the net charge on the conductor is going to be the density times the length, because we're given a linear charge density instead of a volume charge density. And this is going to be the length of the Gaussian surface we picked, because we're looking for the net charge inside the Gaussian surface. So we've got lambda L plus rho times pi r squared L. Let's put our Gauss's law together. The integral of E dot dA is E times 2 pi r L equals our Q enclosed, lambda L, plus rho pi r squared L, all divided by epsilon naught. This one's a little bit messier, but we can still deal with it. We have an L in every single term, so those can divide out. Then I can divide 2 pi r on both sides. Now, we can, oops, I forgot my epsilon naught. We can simplify this a little bit if we wish. I don't think I'm going to simplify it very much. I think I'm just going to take my 1 over r outside, just to make it a little easier to see the dependence on r when we do our graph later on. The direction of our electric field, we know that the charge on the conductor is bigger than the charge on the insulator. We found that out in part A. So the net charge inside my Gaussian surface is negative, so my net electric field is everywhere inwards. Okay, so the next two parts of this problem ask us to plug in some numbers and draw a graph. This video has gotten a bit long, so I'm going to move to another video for that part.